in near second order, which is observed usually like this, in terms of a system which has two kinds of disorder. So there is a point-like disorder, and it's little impurities plus components in the quasi-equilibrium, equipartition regime, which is much larger than the Brunet. And then on top of it, there are long wavelength fluctuations which come from scattering of electron spins on localized magnetic moments. The moments are almost ordered, so there is a very long correlation length psi, and eventually it's going to diverge at t going to Tc. And I guess we are not so much interested in other details of the resistive anomaly, but for me it's an excuse to show how the Boltzmann equation fails, even in rather simple situations. So the problem which we have seems to be pretty straightforward. We have two kinds of scatterers, short range, long range. Lo and behold, the usual Boltzmann equation will tell us that we should add up two collision integrals. And almost immediate consequence of this, almost immediate, is that if I know the scattering time due to short range disorder, and transport scattering time due to long range. So for short range, transport and single particle are the same. For long range, they are different, and we need to use auto transport time. Then the resistivity is going to be proportional to the inverse sum of the scattering curls. Now, why I said that this is almost immediate? Because I have Andy here, and Andy is a student of Shankar, Dassarma, and Shankar knows many things. And one of them is that if the relaxation times are functions of energy, strong functions of energy, which happens to be in semiconductors, then when I'm solving the Boltzmann equation, I end up with a combination of two relaxation times like this, which I have to average over energies with the usual derivative of the Fermi function, density of states, etc., etc. And because of the different energy dependencies here, this is not going to be the inverse sum of inverse times. Okay? But in the Fermi gas, when temperature is very low, we can forget about this. So the addition of our collision integrals in a well-degenerate Fermi gas is paramount to adding up the inverse scattering rates, right? Okay. And now we're going to see that this is not valid, not always valid. And more precisely, it is not valid in the most interesting region for us, that is in the narrow vicinity of Tt, when the accumulation length becomes very long, and in particular, it becomes much longer than the mean-free path due to short-range disorder. Okay, so last time I had the Fermi golden rule formula. I'm going to copy it again. So this is Fermi golden rule for the inverse transport time due to long range disorder. This is equal to pi, we're in 3 dimensions, so I'll have dq u squared. Then I have the transport factor, which we talked about a lot. Then there is a scattering probability. Integrate the principal from 0 to 2kf. And then I will throw in what I call, without giving you any reason, by the interaction time. And if I'm dealing with ballistic electrons, this delta t is nothing more than the angular averaging in the proper d-dimensional space of a delta function which conserves energy. Okay. And we know that by units, it's 1 over energy, it means it's time. If we actually calculate it for small angle scattering, it's going to be 1 over the Fermi Q. Now I'm going to give a physical interpretation to this time. So let's say I have an electron which scatters in such a way that its momentum is changing by amount of q. And we know that by uncertainty principle that cannot happen at one point, right? So 1 over q is the length over which this change in momentum happened. But then 1 over v of q is the length divided by the Fermi velocity. So this is the time which it took an electron to change its momentum. It's not mean-free time. It's not time that we measure, at least in this type of measurements, but it's time which it takes electrons to go from one state to another state. All right, so this is okay as long as electrons move on ballistic trajectory while being scattered by point-like impurities. But suppose that we are in the case when the accretion length is much longer than the mean-free path. Now, because the scale of the momentum here is controlled by the inverse accretion length, this is going to be our typical transferred momentum, right? And therefore, when I need to decide whether my trajectory is ballistic or it's zigzag-like, I need to compare the accretion length with the mean-free path. And if the accretion length is much longer than the mean-free path, my trajectory is going to look like this. So while I'll be scattering by long range disorder, I will move on a diffusive path, right? And so part of this was captured by the original Fisher-Langer argument and then improved and kind of solidified by other authors who said that, well, in this case, what we have to do is to replace the delta function here by some Lorentzian of width 1 over tau s. Because this rate gives you the smearing of the single particle state. And if you do so, you will find that delta tau of q is a constant, and now this time is simply the short-range scattering time. Okay. And this is bad news for the universal contribution to the resistivity, because in the ballistic limit, delta q is 1 over q, so that enhances the singularity. So the integral becomes more sensitive to small q, but according to this prescription, I have to replace it by a constant, which means that the infrared part of the integral gets suppressed. As predicted by, or conjectured by Fisher-Langer, that leads to a weakening of the anomaly predicted by Dijon and Friedel. I will argue, however, that this is not the main effect of diffusion. The obvious effect of diffusion is that the time to travel the same distance, 1 over, is now much longer. And this time is now the diffusion time. Where d is the diffusion coefficient due to short range. So then, we amplify the infrared singularity, and we get a stronger divergence that was obtained by Friedel and Dijon. It's also fairly easy to understand which of the critical indices will enter, because now if I do my power counting, I have a q squared from the transport factor, but the diffusive factor cancels it out. And I simply have dq squared, which is the integral over three-dimensional momentum space of the correlation function, right? The integral over three-dimensional space, the store also angle of the correlation function, is nothing more than the same correlation function in real space, taking at r equal to 0, which is the RMS fluctuation of the order parameter, let's say, monetization. Now, there is an index beta in autocritical theory, such that the average order parameter equals as minus reduced temperature to the power of beta when, well, theta in world when theta is negative, theta is my reduced temperature, T minus Tc over Tc. Here I have two indices of the order parameter. Therefore, I will end up with scaling theta to the power of 2 beta. Okay, so that's going to be the final result. So now the singular part of other resistivity still are contains two. Yes.
Fluctuations get smaller as you approach TC.
Sorry. Fluctuations get smaller. Yes. Fluctuations get smaller because the average order parameter. Sorry, this is minus beta. This is going to be.
Positive.
Yeah. This is positive. Fluctuations become smaller. Because you're going into the ordered state.
Yeah, but this is from above.
Either above or below, doesn't matter. Fluctuation becomes small.
But
Yeah.
are you now working with the limit where delta t is momentum independent?
I'm sorry?
Are you working with the limit where delta t is momentum independent?
No, I'm working in the limit when delta is very strongly momentum dependent. It's 1 over q squared by the diffusive argument.
Okay, so there was this cancellation with the other q's. Okay, got it.
Yeah, so there is this one and there is this one. Okay.
I think that guy should be alpha plus 1. Not
No, so well, okay, so let me show the final result. Can I?
same thing as the
Okay. So this is what you get if you use the correct asymptotic of the correlation function, which is known to us from Fisher, Aroni, Wagner, etc., etc. So you have terms which are parameterized by eta, the spatial correlation, the spatial decay exponent. There is an alpha from specific heat, and there is a nu. But because you have Wiedemann identity, you can combine these exponents into beta, into 2 beta. Okay. Now, we still have two terms, meaning that Fisher-Langer are right, they're always right. So there is our contribution, which I'll write for delta rho as, okay, this is going to be my theta function, not to confuse with theta. So this is going to be sine theta, then this mod theta of 1 minus alpha with some number a. Well, it's not really a number, but a function of all parameters of the system. And then there are going to be a new one, which is a diffusive anomaly coming with 2 beta. And now it's only the issue which one is larger, right? Okay, and it can be either way. But we can also, by using the hyperscaling relation, because we're below 4, we can also relate 2 beta to alpha, and 2 beta is 1 minus alpha. This is Fisher-Langer exponent, minus something else. And if this something else is positive, then the second R contribution wins. If it's negative, then the first R contribution wins. Okay. And for the neutrality R classes, which we all know and love, this zeta is positive, which means the 2 beta term is more singular than the Fisher-Langer term. Right. So talking about transport, so this is kind of sidetrack for me. But now, how does it come out from the real theory, right? Obviously, it's not going to come out from the Boltzmann equation, because in the Boltzmann equation, as we know it, I wouldn't be allowed to mess with this delta function here and replace it by, let's say, some diffusive time, right? Okay, but what should work? Well, we still have diagrams, right? Diagrams should work no matter what. And there are pretty simple diagrams which can be identified to be responsible for the whole effect. And because I assume, I probably told you so, but I should have. So because I assume that my long range disorder is weak, I'm going to do only a perturbation theory with respect to long range. Yes, Josh? It came from? No. So from the Lorentzian, you'll get a constant. It comes from the relation between space and time in diffusion. Space is root of dt. So time is x squared over d. X is the region, is the size of the region of order 1 over q. So you have 1 over q squared, 1 over d.
If you have this short reach scattering that's happening like in your character like much faster than this long range scattering, and is kind of completely shuffling the momentum on a scale that's much larger than 1 over psi, what's the meaning of asking how much time does it take me to relax it, to change my momentum by 1 over psi?
Due to long range. So I want specifically have a contribution which is change of the momentum due to long range, because only this R contribution will contain the singular dependence on unreduced temperature. Of course, main job of changing the momentum is coming from a point like Vespritis, but this is background. What I want is a little feature on top of this background.
And in Boltzmann theory, it makes sense to separate these two.
So if I separate these two, I have no result. I cannot explain the resistive anomaly as it's seen. So Dijon Friedel is our separation of the two, right? Which doesn't work. But I'm trying to do something which has a chance to work. All right, so what are the diagrams? As a reminder, I will have a disorder averaged single particle Green's function. This is going to be my solid line. I wouldn't spell what it is, wouldn't really matter. And so, of course, for the diagram is just a bubble composed of these two functions. That gives me the Drude conductivity due to short range disorder, the usual thing, right? Okay. No vertex R corrections, as we talked last time, because for algebraic scattering, vertex corrections are absent. Then I can add long range disorder in two possible ways. And now let me define the correlation function of short range disorder by dotted line and long range by dashed line. Okay. So think of point here as point-like. This is long dash, this is long range line. Okay. So I can insert long range correlation function as a self energy, and I can insert it as the vertex R correction. And then it's only one because I'm doing lowest order perturbation theory. These diagrams know about two scales. I know about my short range mean-free path. We know about arc psi, and so they have two limits. If I take the limit of ballistic limit, Ls is much larger than arc psi, it does reproduce Fermi golden rule with delta function, and from here, Dijon-Friedel follows. Yes?
Both line is only short range propagator.
Yes, I'm doing perturbation theory. So my short range is hidden in the thick lines, and all my long range is explicitly in front of it. It's not hidden anywhere. Okay, so ballistic limits of these two diagrams is back to Adijan-Friedel.
You know, since you're allowed to include all orders in the short range one, you can include more lines there, right?
I'm just doing it step by step.
Okay.
Okay. If I take the diffusive limit of the same two diagrams, those people who advocated of replacing the delta function by Lorentzian, they were right. So this reduces delta tau to tau s, and leads to a weakening of the Diagrammatic anomaly. However, I'm not done yet. I still have the dotted line, which I can put in. And I can also put it in into different ways. Oops. Too solid line. Didn't want to have it too solid. Okay. I can do it like this. Or I can do it. Action. I can do it like that. Yeah, sorry, no. Okay, here. Okay, so I have this stick made out of points. I can put the stick in, or I can put the stick at an angle, right? And because I'm already detached from the current vertex, because I have long range vertex here, this diagram doesn't vanish. If I would put only one dotted line here, that would vanish, but I have one vertex here. Fine, but if I put one line, why stop here? Let's add infinite number of them. And then what we add is a shaded box in two possible ways. And the shaded box has its known name. It's called Diffuson. It's an infinite sum of ladder diagrams made out of short-range disorder. And it's particle Hall propagated. And it's called diffusion for a good reason. Just this object by itself, if we take it in the small q, small omega limit, let's call this lambda, it has a diffusive pole. Okay. Yes.
Or diagrams full of rainbows of portrait and non-brain crossing each other on a single arm?
I believe that this is all. Rainbows I'm not interested in. I mean, like this, like this.
No, like crossing each other.
No. And the reason is that this is a retarded Green's function, and this is also a retarded Green's function. And if I put in one more dotted line here, then by the usual rule, RR average is equal to 0. This is, if you're familiar with Altshuler-Aronov diagrams, this is actually made out of the same stuff as Altshuler-Aronov diagrams, except for the dashed line in Altshuler-Aronov is the wavy line of electron-electron interaction, which is inelastic. And therefore, in this case, I would have to dress also the vortices. But this is much simpler problem, although I believe it has the same moral of the story. Okay? The moral of the story is that diffusive electrons, by the nature of their slow motion, are more susceptible to any external perturbation than ballistic electrons. And external perturbation can be long-range impurity scattering, or it can be electron-electron interaction. Diffusive motion amplifies everything. Okay. Now, because we're looking at static DC conductivity, I need to put omega to 0. And if I put omega to 0, this whole block, diffusion, becomes 1 over dq squared. And this is exactly the amplification factor, which comes from this hand-waving argument about the diffusive motion. the calculations are trivial. Yes. I don't want to go to 2 because I said that it's weak long range. Okay. Yes.
What was the reason the diagrams above gave delta T equal to tau?
Why? What is the reason? Well, what I simply did, I smeared the fermionic Green's functions without taking into account diffusion. Diffusion as a physical process comes about because of these shady blocks. So here I literally did what people in the 60s said: you need to replace delta function by Lorentzian. The imaginary part of each of these Green's function is Lorentzian. Okay. Yes. Yeah.
But here, when you draw in those diagrams, the Q seems beautiful. With the exchange with the
No, it's the same thing. Maybe I mixed up the direction of the errors, but it's the same internal Q which is being transferred through the. So our Q here always goes through the long range line in all of the cases, and simultaneously through the diffusion.
They should be in function of the horizontal drawing.
Sure. So if you kind of put back this series, then of course here I scatter from some k into some k prime, and k prime is totally unrelated to k because this is a short range disorder. But the incoming state has momentum q extra, and this momentum extra which is what's going into the diffusion pole. Now, of course, this is only the diffusive limit. In principle, I have the whole thing, and that's why I can see that in the ballistic limit, this is not important, but in the diffusive limit, this is the leading sequence of that. Yeah. I said weak. I'm doing perturbation theory, right? I'm not weak, but I'm doing perturbation theory. Maybe I'm weak because I'm doing perturbation theory. Yes.
Diffusion doesn't depend on the order of limits. It's only when you insert that into the bubble diagram.
Well, the diffusion does depend on order of limits. It depends on what goes to 0 first, but.
I meant short range versus.
Oh, no. Well, no. So this order of limits when a disorder is a short range is strong, and therefore all smearing of the single particle states is coming primarily from short range. And then having these short range smeared states, I built up lowest order perturbation theory for the correction to the conductivity due to long range. Okay. Now, omega here is the frequency of light. So if I would be measuring optical arc, optical conductivity, I should keep it finite. Okay. So last time I argued, yes.
These lines are dressed or not really dressed?
These lines? Yes, they're dressed. Yeah. Otherwise, you wouldn't form a diffusion arc coefficient because it comes from short range. So last time I argued that this effect, this resistive anomaly, or the fact that that Adamadian rule is violated, is coming about the classical memory effect. How can I see it explicitly? Well, I can also calculate the optical conductivity, keeping finite frequency, and then I will find that the real part of the conductivity would scale as conductivity absolute value to the dimensionality d over 2, and that's precisely what the exact solution of the Lorentz model gives for the velocity, a correlation function taken in Fourier space, one-to-one. Right. So where is this? Disks here? We don't have disks. We don't have spheres, but we have long-range disorder, right? Long-range disorder with finite size. No, this is for omega, much smaller than diffusion coefficient divided by xi squared.
There's
Oh, yeah, sure, delta. Yeah. Okay, so it's interesting frequency dependence. First of all, it's non-analytic, and second, it's positive. Why it's positive? because finite frequency weakens the effect of diffusion, right? As opposed to 1 over dq squared, if I take the real part of it, I will have dq squared plus omega squared. So finite frequency at first helps the conductivity.
There's the local minimum of the.
Right, so it's going to look like this. We'll start from some value. It will go, let's say, in 2D linearly. Then there will be, so this scale is still much smaller than 1 over tau, because I have 1 over xi squared. Then there will be a plateau, and then at frequencies of order 1 over tau, you will recover the usual omega squared tau. Okay. Whether it can be accessed experimentally, I talked to Peter, talked to other people. Definitely not in nickel. You don't want to do optics at 625 Kelvin. Yes.
How do you get this relation that sigma is proportional to omega?
So I didn't tell you really how I got the static part, but doing these diagrams, calculating them, I can do it at finite frequency, I can do it at zero frequency. So if I do this calculation at finite frequency and subtract off the zero frequency part, that's what I get, right? Okay. Details of calculation don't matter. It's just a standard the diagrammatic exercise. As usual in transport, you have to watch for gauge invariance. You want to calculate a gauge invariance object. Each of these diagrams on its own is non-gauge invariant. It's only the pairs. If you add this and this, and this and this, then they are gauge invariants. And until you get gauge invariance, you'll be getting the wrong results.
What's the
Temperature dependence is interesting. It is characterized by, even here.
Yeah.
Okay, it's minus gamma.
It gets big as
Yeah.
you approach.
Well, it gets big as you approach DC, but at the same time, the range in which it belongs becomes narrow because psi increases. So it becomes steeper, but also confined to a narrow and narrow range of frequencies. Well, if you look at numbers, I don't think that it's very realistic. You need to have some very low temperature ferromagnet with very low temperature ferromagnet. Peter, when are you comfortable with doing optics? At what temperature?
1.5 Kelvin CC.
Okay, but up to what?
Oh, for me, we can go to 300 Kelvin, but you could go to, if you were, people have done 500 Kelvin, 600 Kelvin.
Yeah, well, okay, so there is another part of the story which I wasn't going to go into at all, but there is also a detrimental effect of Coulomb interaction on diffusion. It has no effect on the static conductivity, but it has a detrimental effect on the frequency dependence. I need to make sure that my screening is basically turned off. I can do it, let's say, in two-dimensional ferromagnet which is gated. I can do it near the ferroelectric instability if it's second order, because then the charges are embedded into a matrix which has huge epsilon, and the Coulomb interaction is kind of turned off. So what happens is that diffusion of charged particles, and they have the same charge, they kind of repel each other. Okay. And that changes this diffusion into a screened diffusion, and the singularity in the screened diffusion is weaker than in other barrel. But this is, yes?
Mind arguing again why nothing should happen at omega of order psi to the minus z, where z is the dynamical exponent for the stochastic.
Well, of course, nothing is going to happen in this model because yeah. So in a real model, in real life, something should happen. But I will show you data from Peter, which he told me about yesterday, that the static assumption seems to work. Yes.
How do you check for gauge invariance? Like,
You have to make sure that anytime you have the correlation function, and this is the correlation function, it comes multiplied by something which vanishes and presumably vanishes as q squared. Why? Well, because I can think about infinitely long range disorder, which would be a delta function quantum space. Right? There should be no physical effect due to this long range disorder. Therefore, I should have weight which vanishes at q going to 0. And this weight is coming from the rest of the diagrams, but only after u. Yes.
Let's say that I'm scared of diagrams and I want to hang on as much as I can to Boltzmann theory. So
wonderful.
You had like some justification
Wonderful.
for incorporating this.
Wonderful. I also like Boltzmann theory, as you might have noticed by now. And it was also a great disappointment for me that it failed.
So you had some like intuition for how this could kind of like come into the Friedel Degenet.
Yes, so I know how to fix the Boltzmann equation to get these results.
Is there a way to do this formally?
Formally, absolutely formal. All I do with this is absolutely formal. Right? Okay. Okay. So, what about fixing the? Can we salvage the old good Boltzmann equation? Yes, we can, but we have to go one step back. When instead of Boltzmann equation, we had the Liouville equation. Liouville equation is exact. And again, I'm looking at a single particle problem, but in the Liouville equation, I will have df dt plus v del f plus external force, the time and position dependent, dk, and I will have 0 on the right-hand side. Right? Just motion of particle under the force. So what is this force? Well, now we'll split this force into two parts. One is going to be the force due to long-range disorder. I know it at least for one realization. And the second part is going to be the external electric field, which for the more general case, I can assume to be time-dependent, but all the spatial inhomogeneity is coming from this term, right? And then, well, this is exact, but then I will say, okay, I also have short-range disorder, and I will average over the fluctuations of short-range nature without doing anything to long-range. When we average over fluctuations, we do end up with some kind of a collision integral, and I will recover the collision integral in the form correct for point like impurities on the right-hand side. Okay, so this is known as stochastic Liouville equation. How I should solve it? In principle, I should solve it for a given realization of disorder, of long-range disorder. I will find my function, which is still function of position, time. I will multiply it by the velocity minus charge. Oh, okay. So of course I have the momentum here. Right? I will integrate of the momentum. This is going to be our current at point R, right? And then I will average the current. Okay. So instead of the conventional Boltzmann equation, which from the very beginning operates with averaged distribution functions, I first pretend that I know the exact distribution function and average only at the end. And of course, this is extremely complicated object because it depends on potential profile in U in some very nonlinear manner, right? But okay, I can still try to do a perturbation theory. And if I knew the exact Green's function of this equation, which would be function of k, r, t, k prime, r prime, t prime, I will take the part which comes with the external electric field. I will linearize because I can still assume that the electric field is weak. So this is my disorder part, long range. dot df Okay, let me bring the scattering term on the right-hand side, on the left-hand side. And on the right-hand side, I will have my linearized source term. Okay, so I will find the Green's function, which is the same equation with the delta function on the other right-hand side. I will convolute my source, let's call it source, which is also function of R and T, K prime, R prime, T prime. And that will give me the distribution function, which I will then average. And I will average it in this way. And if I don't do it in this way, there is one more issue. That is, if I don't have external electric field, right, I only have electrons, which are somehow relaxed in some long-range potential profile, but that means that the equilibrium function is a non-uniform function because there is potential energy which reduces kinetic energy. So this F naught in here is actually the Fermi function at energy which is shifted by the potential energy at point R. So I have R also in here. And the Green's function, of course, also has R. And then I will do a perturbation theory for this Green's function in the same way as we do it for any Green's function. There would be a bare one. And then I will have the vertex. Oh, sorry. The vertex, it is this one. Point here, E, and tone doing at any order. Now I want to do second order to make the connection with diagrams, and I can get the second order in two ways. I can expand my Green's function to second order in U, forgetting about U and S. I can forget about U and S to second order, or I can do first order of each and take the cross product. And that actually forms a nice diagrammatic technique for the conductivity. So conductivity alpha beta is going to be given by, so this is line without long range. So this is velocity component alpha, this is velocity component beta. And then I will have three other diagrams. This is going to be my correlation function, gain velocities. And then so you do this for diagrams, and you get the same result as from other Kubo formula. So Boltzmann equation can be saved, but at the expense of postponing averaging. Can also be checked that in the same model, if I would bring in the magnetic field, so last time I mentioned very briefly that the Boltzmann equation tells you that as long as the spectrum of the system, as long as the band is isotropic, there is no magnetic resistance. There is magnetic conductivity, there is whole arc conductivity, but rho XX is flat. Okay. This is because, again, we are forgetting about classical memory effect. If I would introduce anti-Lorentz force in addition to the electric field and calculate magnetic resistivity, I will get non-zero, strong, positive magnetic resistance. Okay? So I believe that we haven't explored all the consequences of this classical memory effect, especially when we start to add electron interactions, right? There is something to be done. Okay. All right, so I just wanted to flash two slides to finish the subject. Okay, so in the literature, prior to mid-70s, there was general belief that Fischer-Langer is the thing. that it always works. From mid-70s, counterexamples started to show up, and usually they are found in non-elemental ferromagnets, rare earth nickel, and this is dysprosium, this is gadolinium. So as you see, there is a cusp in resistivity, Fischer-Langer in cusp in DRO-DT. Here it's even more complicated. You have cusp and then anti-cusp. What actually happens if you add two R contributions, Fischer-Langer and diffusive, you end up with this picture. This is not very informative plot, but very careful analysis of the anomaly in nickel. And what you need to watch for is the deviation of these empty circles from the horizontal line. So when the point is on the line, that means Fischer-Langer works.
What is the y-axis?
It's a residual, so it's data minus theory, or data minus fit. Okay, and this is at reduced temperature, and you start to see that when you get very close to 0 on the scale, there is additional peak which is missed in Fischer-Langer.
So it's depression.
No, it's with minus sign here. Yeah, it's complicated plot, and
It's actual resistance on the far left. Is dysprosium nickel, that's resistance?
except for I don't remember in which units. Yeah, I need to look it up in the original paper. Okay, and this is what Peter told me about yesterday, and I missed this paper. I should have, of course, seen it. So this is a ferromagnetic member of the ruthenate family, calcium-2 ruthenium 4, which has under pressure, as far as I understand, strain. It has a ferromagnetic transition at 10 Kelvin, so that's low temperature ferromagnet. But and if you compare the anomaly on this rho versus T plot, it's not very pronounced, much less than in nickel. But what Peter does with his wonderful techniques, he measures two rates, the momentum rotation rate, which is 1 over tau we're talking about, and the energy rotation rate. And you see that there is a clear cusp in the momentum rotation rate. Okay, this is the feature of other diffusive anomaly. At the same time, coming back to your favorite question, the energy rate goes through TC without barely noticing. Okay? So I don't have a theoretical answer, but this is the answer from Peter. All right, I'm done with the first part, a disorder, and I'm ready to move to electron-electron interactions. Any questions about a disorder? Let's ask them now. Yes?
What does anomaly refer here?
Anomaly refers to some feature at TC. This one or this one. Well,
Not centils.
Why not just calling it singularity or singularity?
Well, I need to go back to 1932, call the spirit of Gerlach, and ask him to rename it. Yes.
Phonons that are faster than the Fermi velocity. So
Oh.
I don't have short-range scattering from phonons.
Faster than the Fermi velocity.
Yes.
Then I will never get into the Abloh-Grüneisen range.
So there will be no resistive anomaly?
No, there will be certainly resistive anomaly in the sense that, okay, I will have more complicated background of resistance because I will be in the inelastic regime of electron-phonon interaction, right? They would not act as point-like impurities. So instead of 1 over tau short, I will have to use 1 over tau transport. But still, it's not going to be singular.
But I can still have short-range scattering from the magnetic.
It doesn't really matter. The fact that the first type of disorder was short range didn't really matter, right? I can build the diffusion out of finite range correlation function. But I still want to have Xi to be longest scale.
So it just complicates my analysis.
Yeah, but at the end of the day, we know that no matter what the scattering R potential is, you do end up with the diffusion coefficient, which contains appropriate transport time. Yes.
How do you explain that last law?
How do I explain this last law? Well, so according to our understanding, the diffusive anomaly has a cusp in the resistivity. That means that the scattering rate has a cusp. Okay, so this is the cusp in here, right? Now, the energy utilization rate is an a priori justification of the assumption that I can treat magnetic fluctuations as static. Okay, I chose to do so despite vigorous complaints, but this is kind of a posteriori justification that maybe that's not too bad, that a critical slowdown works. Okay, well, since I have my screen up, right, so actually this is part 2. Okay, so I wanted to talk about, originally about Fermi liquids and beyond. I will end up not doing this, but I will talk about transport in conventional Fermi liquids and also in strange Fermi liquids. So there is a new guy on the block, a strange Fermi liquid. Okay, and I collaborated on this subject with lots of people, out of which Josh Arkovi is here, and he's going to present a poster next Monday, right? But there are former members of the group, current members of the group, fairly unknown junior scientists such as Andrei Chubakov and Alex Arkamenev, all these youngsters. And okay, and I wouldn't list the papers, the subject. Okay, so here I have almost random collection of t-squared behavior of other resistivity, which we expect from a Fermi liquid due to the Pauli argument, which of course you are all familiar with. And I intentionally threw in several examples in which we think we understand the t-squared behavior to be contrasted with other examples where we don't understand. Okay, so let's start with something very simple. This is aluminum as a function of t-squared. So I didn't put a reference. There's a reference in the lecture notes. And without even going into details, that's what we would expect to see. It's aluminum, it's a large Fermi surface, large number of electrons, club scattering, of which I will talk later, but you probably heard of this one way or another, is allowed. There is no reason for aluminum not to have t-squared. This is another example. This is cerium aluminum 3. This is a heavy fermion metal. Same story, large Fermi surface, clubs are allowed. And there is a range of t-squared, but if you look at the units here, you will realize that it says here in the caption is that this is seen below 100 millikelvin, 0.1 Kelvin. And the range of t-squared in aluminum is also not very impressive. So this is t-squared. So this is 2 Kelvin, and this is root of 8, few Kelvin range. And then we have other examples, and probably historically the first one was t-squared observed in strontium titanium oxide, or doped strontium titanium oxide, and historically it means that it goes back to 1950 something, right? But people didn't pay any attention to this t-squared, ascribing this habitually to a Fermi liquid, until the seminal paper from Cameron-Benny group came out in 2015, who didn't measure anything new. He measured DC resistivity. He saw a t-squared term, but what he said, look, guys, the Fermi surface is a tiny drop at the gamma point of the Brillouin zone. There is no way collapse can happen under these conditions. How come we're seeing this t-squared? Of course, he said more things, but this was the main message. This is interesting material. It's quantum paraelectric. There's lots of physics going on in there. There are soft phonon modes. Some theorists, including myself, came up with theories that this T squared is actually not electron-electron. It's actually electron-phonon interaction of a two-phonon type. These are details. I don't think that we have the full picture. But there is another guy on the block, and I think Cameron specifically found this one to have something which is plain vanilla. Because when the story about HTO came out, well, this two-phonon story also came out, and Cameron found something which is totally safe from any theoretical assumptions about phonons. It's not a paraelectric. It doesn't have soft phonon modes. It's a simple, conventional, extremely boring semiconductor with tiny Fermi surface, almost spherical. Spectrum is almost parabolic at the gamma point of the Brillouin zone. And yet, it shows T squared, which, by the way, makes T squared in conventional Fermi liquids to be pale in our comparison, both in the width of the T squared term and also in other magnitude. So the resistivity changes here by at least order of magnitude. Okay, this is another story, which is, as you see from other plot, this is very old plot. This is bismuth. And what is plotted here are mobilities separately for electrons and holes, because bismuth is a canonical example of a compensated semimetal, which is a metal with electron pockets and hole pockets, such that the number of electrons is strictly equal to the number of holes. Okay, T squared in here, well, T squared, T minus 2 in other mobility is the same as T squared in other resistivity. And this is also an example which we understand. I'll be talking about this electron-hole scattering in a compensated metal does give rise to T squared. Okay? And very recently, 2025, there is one more addition to the family. This is quantum well, two-dimensional electron gas in mercury telluride. It's a well-known system, but they doped it, well, gated it pretty high, so they are away from the Dirac cone and measured the up resistivity. And again, you see T squared, strong, 1.5 order of magnitude variation. Same story, it's tiny, tiny Fermi surface, no Ohm collapse, you have T squared. And finally, this is the data which Josh and I are still working on in our collaboration with Denis Bandurin group. This is twisted barrier, our graphene, away from the magic angle. This is 2 degrees, so it's not a superconductor. And the T squared in the wide interval of number densities, both above and below the charge of neutrality point. And you can notice that, as you increase the density, you go this way, meaning that you're getting closer to 1/2 our singularity, then this T squared is replaced by linear T at high temperatures, right? And now this is part of the old story and part of the new story, because as you will see from Josh's plot, there is a region of densities where Ohm collapse scattering on the superlattice is allowed. This is superlattice. The period in real space is much longer than the period of lattice in monolayer graphene. Correspondingly, the Brillouin zone size is very small. And so even at moderate number densities of 10 to 12 per square centimeter, you can satisfy the Ohm collapse condition. However, there is also a region of densities where it cannot satisfy it, and both show T squared. There are different T squareds in the sense that the coefficients of these two T squareds behave differently as a function of number density. And I think we understand the Ohm collapse T squared, but the non-Ohm collapse T squared belongs to the family of strange Fermi liquids. Okay, and if I gave you some resolution or quasi-resolution about the resistive anomaly at the end of the day, this is my super goal, but my super goal would be to, being boring academician, separate or classify all possible sources of known T squared behavior, only to conclude that none of them can explain some of these examples. And so we have a real problem on our hand, if we cannot explain Fermi liquid, that's something we need to worry about. Okay? All right. So this is my super goal. And now
Can I ask a question?
Sure.
Of these examples, where do you think the most kind of the best experimental example for T squared is? So I remember in STO, it's.
I think most clear is this semiconductor, bismuth 202 selenium, because it's so boring. You cannot invoke anything.
That's good from a kind of a phenomenological perspective, but where's like the data the best, largest railing of largest scaling. of T
So
squared, same thing.
in terms of T squared, this is excellent T squared.
Yeah, okay.
There is no fudging. This comes from Benya. Okay, so it's the same, or it's the same quality T squared as an STO. Same range. Well, low range, but up to room temperature. Okay, from helium. And I think this data for T squared in mercury telluride is also very clean, as well as T squared in TBG.
I mean, I should know this, but like in a clean gallium arsenide 2-deg,
Yeah.
it's T to the 5th?
Well,
Or what's it there?
let's say it's T to low temperatures because Bloch granizing is low, and then it's nonlinear, right? And this nonlinear, yes, you can fit it into T5, you can fit it into T4 plus T5, because whether it's two-dimensional phonons or three-dimensional phonons, it's not very clear. No, T squared you wouldn't see. No, gallium arsenide is as good example of a Galilean invariant system in solid state as it
I
will be.
think mercury telluride's just as good.
Yes.
Or, I mean, more or less.
Yeah.
Those densities are not high.
Yeah. Yes.
I know for TBG it's the case, I think it is for bismuth and STO, but not only do you have T squared present for low density, but it actually grows. The coefficient actually grows with lowering densities.
You mean in TBG?
TBG and correct me if I'm wrong. I think the coefficient T squared increases decreasing density. Not only is it present, but actually.
No, so coefficient of T squared in the semiconductor in STO, it goes down almost as 1 over the number density. But this is kind of to be expected because we're talking about other resistivity. If you think about the other resistivity in the Drude formula, it has 1 over n, right? Which means that the remaining density dependence, if it's coming from the scattering time, is almost not there. So this T squared also has a feature of being density independent, which is one of the counter arguments why this T squared is a Fermi liquid, RT squared.
Maybe even asking for a more boring example, what's the best data set of a true Fermi liquid?
What do you call true Fermi liquid?
Something where the density is large enough.
Aluminum. No, that's strontium orthogonate. Yeah, strontium orthogonate. Yeah, low temperature in strontium orthogonate. But in conventional metals, in good metals, it's very hard to see T squared, right? So we kind of born with the belief that if we take a piece of copper and we measure its resistivity, we'll see T squared. No, you will not see T squared because it's just masked by other contributions. Because phonons.
Is it clear why you can see it in aluminum? I didn't know that it was T squared.
You have data where you see it. You have carefully chosen interval where T squared is seen. But by and large, if you just take elemental metal, good chance to find T squared. And of course, the perfect example of a Fermi liquid would be helium-3. And you do see T squared in thermal conductivity and viscosity. You cannot measure charge resistivity of helium-3. Right?
So if you extend aluminum beyond this small range, it goes T to the 5th?
It goes to a mixture of T squared to the 5th, and actually pretty early, at 50 kelvins, it starts to be linear because the Bloch granizing temperature is not that high, and there is this magic factor of 1/5 or 1/4 pure number, which shifts the actual Bloch granizing towards low temperatures. So this myth that Blue-Green is 300 Kelvin or so. No, this is a myth. Even in real materials, this is about 50, 70 Kelvin. I wish Shankar was here, but he likes this point. Okay, so let me start my boring classification of how things should have been. Okay, and I will start with the preamble of what we can possibly expect from theory. Because sometimes we say, okay, T squared, that's Fermi liquid theory, that comes from Fermi liquid theory, and that's not true. Fermi liquid theory doesn't have T squared. If you read the original paper by Landau, 1958, it starts with very characteristic for him opening. It is well known that 1 over tau in a Fermi gas scales is T squared. No reference. I think that that reference goes back to Mott, and that was done in something 1930 something. So for Landau, it was just given fact, and he used this fact to say that the lifetime is not simply long; it's infinite. Landau theory does not deal with interactions between quasi-particles. The interactions between the original particles are being used to renormalize the quasi-particles to make them heavier or lighter, make the G factor to be different by 2, but it deals only with thermodynamics. And in thermodynamics, this is a theory of a Fermi gas with renormalized parameters. And the only thing which differs it from the Fermi gas is that it has a collective modes. If it's neutral, it has 0 sound. If it's charged, it has plasmon. If it's placed in a magnetic field, it also has Cillian modes. Okay? Otherwise, it's a gas. Right? Now, gas is a very good model. We know how to solve good models. Unfortunately, transport of ideal gas is meaningless. We have to take into account the interactions beyond the Landau scheme. Okay? And speaking in terms of the original formulation by Landau was via the Boltzmann equation, the kinetic equation, as it's also known. Which had some terms familiar and the same as in the usual Boltzmann equation. But the fourth term was unusual. The fourth term contained the external forces, whatever they may be, but it also contained a gradient of the quasi-particle energy, which I will tell you just in a second what it is. But the right-hand side of this equation is equal to 0. Yes?
What you call Landau functional there?
It's here. So this delta epsilon is a function of momentum, position, and time, is related to a corresponding change in the distribution function via what is known as a Landau function, not functional. This is a Landau interaction function. Okay, so this is a self-consistent equation on delta F, because only delta will enter here. And at the end of the day, you can parameterize the entire thermodynamics and collective modes via the harmonics of this function in the charge and spin chart. Yeah, you can also do that energy. Yeah, but it's this interaction, because when you take the functional derivative, you'll be left only with one delta F, right?
Okay, I mean,
yeah,
I could also just.
No, but see, this is force. This is force. This is not these are not arc collisions. This is self-consistent force acting on all. So this
again, is so something still called a Hamiltonian. So there's a kinetic energy term times the density of quasi-particles plus the density squared term.
Right.
So usually when I see density squared in the Hamiltonian or effective Hamiltonian, I say that's interaction.
Well, this interaction, but this is, if you wish, will only give you the real part of the self-energy. There is no imaginary part of the self-energy here. The imaginary part of the self-energy would enter through the collision integral. Again, these are the virtual processes.
But it's normally dispersion.
Yeah. So that's why
By interaction.
that's why this term is responsible for the effective mass minimization, G-factor optimization, etc. But the lifetime of this quasi-particle is infinite, meaning that the imaginary part is equal to 0. And this is not good for transport. And because this is not good for transport, we have to, if we stay within the Boltzmann equation formalism, add some collision integral. But by this, the beauty and simplicity of Landau theory is now gone, because I cannot write a completely general form of the collision integral, and I cannot, in general, express this integral in terms of the same, which paranormalize thermodynamic properties of the Fermi gas. By nature of then, I'm bound to some perturbative statements, or I have to rely on numerical simulations. So when you hear something like transport theory of Fermi liquid, it doesn't exist.
But sorry, why can't you not put from Fermi Golden will put in
Oh, then it's going to be, then it's going, I can and I will, but this is not a general statement. I will have to be perturbative. Fermi Golden rule is Born approximation.
but everything's, I mean, when you were doing phonons and disorders.
Sure. So okay.
What's not perturbative?
Okay. So all statements about transport in a Fermi liquid is as perturbative as statements about electron impurity and electron-phonon interaction. Electron-electron interaction is not different, right? Okay. And if we have problems with electron-electron interactions, it may be due to the fact that we don't really know what to put in here, or to what order we need to go here.
This is what gives you T-squared.
Yeah, but for wrong reasons. None of the systems here, which are in color, are supposed to give you T-squared. Yes. Right. Okay. So having said that, what can we say in general, at least? Well, there is certainly one very general and simple statement, is that if a Fermi liquid is Galilean invariant, and it's charged, its conductivity isn't. And it's not even the right statement. More precisely, if you apply an electric field to such a system, it will behave as if which is being accelerated by the applied electric field, because as we know from second law, internal forces in the Galilean invariant system drop out. Okay. So why do we care about Galilean invariant systems? Well, of course, we have lattices, but several systems in this family, they can be approximated by almost parabolic spectrum with the center at the gamma point of the Brillouin zone. So approximately, they are Galilean invariant systems. Out of this, B2O2 selenium is the most parabolic. Okay. Now, I wouldn't repeat the classical argument, but let me tell you how it works out at the quantum level. Again, you've probably seen this. So first of all, I need to define the current. Okay, so let's say I have a Hamiltonian plus. And the interaction term of this in this Hamiltonian is of the density type. N is my number density operator. Okay. Then when we derive the continuity equation, we commute the density with this Hamiltonian, and because the interaction part contains densities, this term drops out, and the current by itself doesn't know anything about the interaction term. And I'll be looking at a current at external momentum equal to 0. Okay. Okay. But now if I want to calculate the time derivative of this current, which is another commutator, G, then on the contrary, the free term will drop out. And from the interaction term, I will get an interesting combination, which will look like this. So there will be interaction there. And then essentially I will repeat the same structure as my interaction Hamiltonian, which I will spell out explicitly this time. So this is 2. But at the velocity, which is at the group velocity so far, will enter as the sum of the velocities after collision minus the sum of the velocities before collision. And because the velocity is proportional to the charge current, this is the imbalance of the current or change of the current of two electrons during one collision event. Now, Galilean invariant system, by definition, is a system with parabolic spectrum. The mass does not have to be the free mass, but it has to be proportional to the square of the momentum. And velocity, therefore, is momentum divided by the mass. Now you see that if you stick it in, the whole bracket cancels out, and we get 0. Well, that's really the only thing which we can say at an exact level, right? Everything else will have to follow from, let's say, Boltzmann equation or Feynman diagrams. Yes? Of course. So as long as Vk is not equal to K over M, and the system is not Galilean invariant, I cannot say anything. Or even if I have two Galilean invariant systems, but with different masses, overall, this is not a Galilean invariant system. So I can have a two-band system or two-value system, right? And all of the systems are not protected by conservation law from electron-electron interactions to influence the conductivity. And so then we have to deal, then we have to go into more details and ask more precise questions, but within a more limited framework. Yeah.
Suppose I have K square over 2m plus K to the 4.
Okay.
Momentum is still conserved.
Yeah.
Current can mix with it.
Yes. So as long as it's not K squared, this part which is not K squared will break our
Galilean invariance.
will break Galilean invariance.
Surely the current can't fully relax yet.
Okay, that certainly that will be certainly the case, but it doesn't follow from here. From here, I can only say that if V is not K over M, in general, current is not conserved. Whether it can be relaxed due to electron-electron, it's going to depend. It depends on types of the spectrum and on whether the system is compensated or not. Yeah.
Let's say there's no other symmetries.
Yeah. So yeah.
Surely the DC conductivity is still.
Well, not in the compensated system.
Right?
Not in the compensated system.
So then there's a particle.
Yeah. So I'm going to prove your statement that even if the system is as non-Galilean invariant as we want, totally anisotropic, but we don't have umklaps, electron-electron interactions cannot render the conductivity finite on their own. However, this will be done within the Boltzmann equation. Yes?
Why this interaction and not like Coulomb, for example,
I,
then Coulomb?
I didn't say anything about what U of Q was, right? Can be anything. Well, screen Coulomb is not a good thing to put into the Hamiltonian because screening should, you know. So think about U of Q as bare Coulomb. The form of the interaction here didn't matter. Okay? What mattered is that we have this combination of velocities, which will show up time and again, either with the Boltzmann equation or with the diagrams. We always look at the same object, the change of the velocity. 5 minutes or 0 minutes. 10. Okay. Yes. Why did I use what? It didn't.
Use velocity.
Sorry. Velocities. Yeah. U is still there. So it's basically a convolution of the interaction part of the Hamiltonian. And of course, I have to sum over the momentum of fermions, right? But it's multiplied by this weighing factor, right? So it tells you how efficient is the interaction in relaxing the current. And it can be as strong as we want, but if the system is Euclidean invariant, you will have U of Q multiplied by 0.
The derivatives of the EK, epsilon K arise under commutation.
You have, so if you look at, yes, so if you look at epsilon, at J at finite Q, you have plus Q minus epsilon of K divided by Q, so you go to slope. Yeah. Right, okay, thank you, Leo. This concerns only uniform current. There is no conservation law for a current which is measured at finite Q, and that means that the conductivity even of a Galilean invariant system is finite at finite Q, and we can calculate it, and we did. And the real part of the conductivity is, of course, proportional to Q squared, because it should vanish at Q equal to 0. It's Q over omega squared in the limit when Q is much smaller than omega over D. Plasma damping, for example, comes from here. Right, plasma damping, you damp plasma at finite U, so it will be damped even in a Galilean invariant system. Same about zero sum. All right, so well, probably in the remaining 2 minutes.
This non-zero, they cancel, right? But this velocity.
No, but this form, okay, sorry. Let me call it different Q. This is external Q. I'm measuring at Q. This Q is momentum transfer. Sorry, yes. So external Q. Okay, so I'll probably just spell out the Boltzmann equation, or at least our collision integral, within which I'll make other statements. And the collision integral, at least within Born approximation, has a very intuitive form. We know that intuitive forms can be dangerous by now, right? But still, let's stick to the intuitive form. It looks like this. So let's say this is the collision integral, which is acting on this on particle momentum k, and it describes collision between particle momentum k, momentum p, k prime, p prime. So I'm summing over k prime, p, and p prime. There is some scattering probability, which I assume to be known. And then we just hook up the Fermi functions in a way that we satisfy the Pauli principle. This is the loss term. And the gain term.
One coming in.
Two coming in, two coming out.
Both equations like a single particle.
It's not single particle anymore. Well, so I said that, right, so I'm following the story of particle with momentum k.
That's what I mean.
Right.
So
Right, but this is still four fermion interaction, which is described by this Hamiltonian, right? We just left one momentum free.
But it's a decay. The right-hand side is a scattering of a particle.
Right, so this is df dt at momentum k is equal to this. Yeah. But this is
Particles of momentum.
yeah. But this is scattering. This is the scattering probability, which you can calculate by using Fermi golden rule from the fourth fermion Hamiltonian, and momentum k enters here. Okay, at this level, we probably don't see anything, right? It's way too complicated. So now I have these Pauli blocking factors. Well, because this is inelastic process, and I have no reason to discard them. And at least if you derive the Boltzmann equation in Keldysh technique, which you can do to lowest order in the electron-electron interaction, that's the form that you get, right? No one tried to go beyond. Way too complicated. Okay? All right. And then the next step is we say that if we're looking at the system in a weak electric field and uniform electric field, the deviations of the actual functions from the distribution function are going to be small, and there is a convenient way to parameterize this. We'll say that f of k is equal to Fermi function times some combination, which has this Pauli blocking form, times some other function of g. And g in magnitude is much smaller than the typical value of the Fermi function, right? And this is, of course, just an arbitrary choice. But if you would do this, the collision integral acquires a very nice form. Namely, I have product of equilibrium functions. And then this little g guy, which measures deviations from at equilibrium, enters as sum of them at momentum k prime plus momentum p prime minus g of k minus g of p. And I have a scattering probability kp k prime p prime. And you see that the order of terms in this non-equilibrium part is the same as order of the velocities in the time derivative of the current, and this is going to be very important. So that this is coming from other source. Okay, let me stop here, and we'll pull out some consequences of this equation of next time.
So why can't you have a term like if not k prime, if not p prime, and then 1 minus if not k?
In here or in here?
Second line, the last one.
Here.
Yeah.
Or this line, the last one.
Yeah.
Okay.
Like
What-
you have just fk, fp, and then 1 minus f prime, right? Why not the other term?
Yeah, so this is the initial state, kp, these are final states, k prime and p prime.
It's like from kp you go to k prime, p prime. Right?
Yeah, so, or you don't know which way you go, right? Because this is time reversal asymmetric, but you can symmetrize it in this form.
Like the first line has like kp go to k prime, p prime, and k
Yeah,
prime, p prime.
Yeah,
goes to
so
kp, right?
this is the process in which you particles with momentum k. This is the process where you gain particles with momentum k. But when you uplinearize, everything is reduced to this. So these are equilibrium functions. These are still non-equilibrium functions. And the non-equilibrium part is only here.
Should that be 0 for a Galilean invariant system? Or
No. This is a non-equilibrium part of the distribution function in the presence of the electric field, right? And it is there. It is affected by electron-electron interactions. And if we applied not the electric field, but we applied thermal gradient, we would have finite thermal conductivity because there are no constraints on thermal transport. I can also apply a shear to my liquid and look at the viscosity, and it's also going to be finite, as in helium-3. But when we apply the electric field, things differ because electric field is a Hamiltonian force. It comes through the Hamiltonian. Thermal gradient and shear are not Hamiltonian forces. You cannot put a gradient of temperature into your Hamiltonian. Cannot write it in terms of A daggers and A. It's a big problem in thermal transport. You have to come up with some ingenious tricks, such as Plottinger came up with some pseudo-gravitational field, but by dealing with charge transport. Yes.